Welcome everyone. This is our section on about quantum computing methods, and today we are really excited to share this talk with Dr. Enrique Galvez, or Dr. Kiko Galvez. I like your nickname. And today the talk is about quantum interference of light. We are really happy to be here with different sponsors as Quantum AI, Association Quantum, Orion X, Baylor University, Q Mexico, Q Poland, and more sponsors who are in this event. As part of the moderator's team, I would like to say if Helen wants to say something.
Okay, sure. Let me share my screen.
Sure.
Okay. So let's talk about our sponsor. We have Q Poland, we have Q Egypt, Q Mexico, Association Quantum, Orion X.net, Minnesota Quantum Computing Meetup, the Toronto Meetup Group, Alexandria Quantum AI Foundation. And our December event will be with Dr. Kipper, Shaki, and Chris Bishop, and this one with Seth and Danica. And today, this is the event with Dr. Galvez. So can Sebastian introduce himself?
I'm Sebastian Zając. I am a physicist, and I study also something about data science, and it's very pleasure to be with you here today.
So let's begin our event with Dr. Enrique Galvez.
Okay, so thank you very much for the invitation to give this this seminar, and I'm gonna talk about quantum interference of light. Is a very interesting topic that I've been working on for a few years. So let me tell you a little bit about what I'm going to be talking about. First, I'll give you a little introduction, some talk about quantum interference, and then I'm going to go through various types of situations: quantum erasing, two-photon interference, entanglement, and QKD. And then finally, talk about remote labs, which has been a recent adventure of mine. So let me just put there a little bit the subtext of this talk. And it is that really quantum interference is really at the core of really a future technology. And then right now we have all these emerging technologies such as quantum communication. Already there are commercial systems for this, and then is the technology is normally called quantum key distribution, or QKD. And then you have quantum teleportation. And then, of course, we have quantum computing, which is really a global race to who gets a big a quantum computer to do new and interesting things. And there are already three companies that have made inroads into this. I list there: D-Wave, Microsoft, and Google. And then there's quantum imaging, and among that you have ghost imaging, and then various forms of entanglement of images, and then quantum metrology, which involves then making measurements in some way where there's a quantum advantage to doing those measurements. And well, another part of say my agenda here is that really we need to educate a future workforce about the fundamentals of quantum mechanics and quantum physics. And you have all these technologies that are rising, and so we need to think about education. And then that involves creating new textbooks, new courses, new curricula. Well, quantum information really requires mostly linear algebra. Even though physicists would grumble at this comment, but in reality, when we're talking about manipulating states, we really need linear algebra, and we don't really need to solve the Schrodinger equation of quantum mechanics as a necessary step. So because it's linear algebra, there's an opportunity to reach out to other branches of science and engineering. So, but what is important is that we need to learn the fundamentals of quantum physics. So even though the physics is well known, the fundamentals perhaps are not so well known, or at least we need to emphasize them. And superposition is a really important one. And I point out, it is a real phenomenon. It's not something quirky about the theory. And quantum information relies on that. And then closer to what I do is that we need to develop not only courses, but also laboratories. And I've been involved in creating a laboratory platform for experiments. And I'm going to be showing you data that involves, let's say, it has been taken within this framework. And one more thing is that these laboratory experiments probe fundamental questions and also applications. And then the equipment costs, I call them inexpensive, but it is inexpensive in the sense that you don't need a huge laser and a huge laboratory, but there's still a cost for the components. And the apparatus can be tabletop, and as you will see, with remote operation opportunities. Okay, so a little bit more about the labs. And then there is really a series of efforts by various people to develop these laboratories, and and really I'm going to be discussing quantum interference in that context. And then we start with twin photons that are created by some process called spontaneous parametric time conversion. Some obscure kind of name, but that is the process. But we create two photons and we do stuff with them. And then now these photons are correlated in energy, momentum, polarization, spatial mode. So there's a lot that we can do with these photons. And then we can do two types of experiments. One type of experiment is single photon experiments, where one photon tells us that the other one is there. Turns out that if you attenuate the light from a laser, you don't get single photons, or at least you don't get single photons all the time. They come out in random sequence, so it is very likely that at any given time you have two photons or three photons together. So you can't really say that you have single photons for sure when you use an attenuated laser. But then these experiments with single photons, where you create two and one tells you that the other one is there, then that constitutes a source of single photons. And then you have a bunch of experiments that can be done with those, and I show some references of educational articles. AJP stands for American Journal of Physics. So it's a journal really devoted to physics education. And then you also have experiments that involve the two photons together. And then there you also have a world of interesting quantum phenomena. And among them, of course, entanglement, which is really a requirement for quantum computing. So I'm going to show you a little bit about that. And also there's two photon interference. And then all these are not purely, let's say, abstract questions. We can apply them. So for example, you have quantum key distribution, and I'll tell you a little bit about that. There's also ghost imaging, which is pretty fascinating topic, which can also lead to applications. And then one more thing, these experiments really do not require quantum optics experts. You can create these photons pairs with not much expertise. And then from then on, then you can decide what you want to do with them. And of course, you need to figure out that part. But at least you don't have to think that you require this immense laboratory just to make photon pairs. So let's get to the topic or the subject of this talk, which is quantum interference. Then we start with a quote by a famous gentleman here in physics, Richard Feynman, who said that superposition is the only mystery of quantum mechanics. And really, if one thinks about it deeply, it is a mystery. And so this is how Richard Feynman defines it, which is in a very thoughtful and intuitive way. And goes as follows. If an event can occur in two or more indistinguishable ways, then the probability of the outcome is the square of the sum of the amplitudes for each case. So very general, you have that an event can occur in two ways. So you have one way and another way. And then now this little bracket thing is a physics thing. It's called Dirac notation. And but basically you combine the two ways in a mathematical form, and then you add a phase in between these. And so the absolute value square of that is the probability of the outcome, which is 1 if the phase is 0, or a multiple of 2 pi, and 0 if the phase is pi or an odd multiple of pi. So you have really stark outcomes for this. But now, if the possibilities are distinguishable, then there's no interference, and the probability is a constant. And then these simple guidelines are very important, especially in quantum information, because we want to create situations where there's superposition and when there's quantum interference. So let's start with one type of quantum interference and superposition with the interference of light. So think about this. We have an interferometer. There we have an interferometer that's called Mach-Zehnder. And we send a photon from A to B. So then if the arms have nearly the same length and have no distinguishable features, then the probability for a photon to go from A to B is a superposition of going through both paths. So after some algebra, then we get that that's the probability, where delta is really related to the phase, thinking of the light as a wave, due to the difference in paths of the light going through both arms. But now, if the paths are distinguishable in some way, and this talk I'll tell you about those situations, then the probability is just 1/2, and constant, independent of this quantity delta. And then that's what distinguishes it from really interference, because here the variation of delta leads to variations in the probability. So now I mentioned linear algebra. So here's an example of how we would analyze this same situation with the linear algebra. Now, if you're not an expert in quantum physics, linear algebra, don't worry, it's not, I'm not going to keep going with this. But here is the idea that then you define that the light going in the x direction, and normally represented by this ket, this quantum thing. And so inside there, the x is really a label. Inside you have all the information about this photon going along x. But now we represent it just by a vector matrix, 1, 0. And then the same thing going along the y direction is this ket with all the information, which we represent as 0 and 1. And the thing is that we're not going to be doing much with what's inside. What are the photons? The only distinction is that one is traveling along x and the other one is traveling along y. And there you have your interferometer. And so then the light hits a beam splitter, first thing it does, which is some optical element. So when we, if the two possibilities are vector matrices, then since the beam splitter puts the light in a superposition of going in the x direction and the y direction, then we model that by a matrix. And then we have the mirrors, and the mirrors are another matrix. And then the interferometer phase, this is more to account for this path length, is also given by a matrix. So you consider now the interferometer in full, then you multiply the matrices, and then there's your linear algebra. And then here you have a matrix that is the interferometer matrix. And then comes the physics, of course, at the end, where we say, well, what's the probability of getting to B? And then you have this thing called the expectation value or the probability of starting in X, being operated by the interferometer, and then ending in X. And then again, that's your physics, and you get to this answer, which is the same one I mentioned earlier. But I say this just in the context that we could make this quantum information very accessible to, because linear algebra is much more readily accessible to engineers, computer scientists, and so on. So, but now let's go back to the experiments. So to the experiments, we need to get single photons. And so then I mentioned this source, parametric down conversion. And so we generate photon pairs. And they follow the laws of conservation of energy and momentum. So here you have the pump photon. That's the energy of a beam of photons that comes into a crystal. And then in the crystal, the two photons are generated. And then the only restriction is that the sum of their energies be equal to the energy of the parent photon. And we call that energy correlation. And then there's some subtlety in this correlation, in that the condition is that the sum is the same value, but not exactly the individual values. And you can get entanglement for that situation. And in fact, I would say that all experiments with parametric down conversion involve energy entanglement, only that entanglement is not used. So a lot of times it's called correlation, but one could use a real entanglement. And then there's momentum, which I represent by letter K, and then momentum is conserved. So there you have it. And then the photons come out in a cone, and then there's a picture of the cone. And the photons that are opposite from the center of the beam, they are the partners. So you have a lot of partners, right? And in the end, the experiment, we waste a lot of light. We only select these photons that are in the horizontal plane. Now, one thing to emphasize here, this is a little bit more about this particular source of light, is that spontaneous parametric down conversion is robust. That is, you don't have to wait for the planets to align for this to happen. You send the laser, and your crystal has to be the right one and at a certain correct orientation, and it'll happen. So that's important, because it is a reliable system. Now, the only thing, though, is that there is a challenge to do with alignment, because you won't see the photons. There's too few of them. Well, we want to do single photon experiments, so then the source is very weak. So then we have to worry about how we align the detectors, interferometers, whatnot, given that we can't see the photons, okay? And there's some tricks to play, but all I'm saying is that there's some challenge in the initial alignment. Once things are aligned, then this is a very reliable platform. Okay, let me say some more about this platform. Again, this is, again, my angle, which is to create affordable systems. So we start with a laser, the pump laser. We're lucky that we have a technology for video recorders, the Blu-ray players, that have made these lasers really inexpensive. This is the gallium nitride diode laser. And again, they are the lasers that are in Blu-ray players. And when that's the first laser that I got with my grant way back. And then it can cost about, that one I spend about $5,000, but then you don't really need that one. You can buy a more inexpensive one. Well, this is between $500 and $1,000. And this has nice current control and it's somewhat reliable. But you can also get a laser pointer. And I've done experiments with a laser pointer, and it's a $20 laser pointer. And of course, they're not terribly reliable, but you can do an experiment, quantum experiment with those lasers. And okay, then comes the crystal. Again, I'm giving prices. I've given this talk to a crowd that wants to do these experiments, but I think it's important to share this with you in case you're interested as well. So, and then there's a company that sells the crystal. We don't need to know the nonlinear optics of this. We just buy it off the shelf. And then the apparatus is not in an optical table, it's an optical breadboard. So it's not that expensive. And it's about 2 feet by 5 feet optical breadboard. And there you have it. That's one of the kind that we use. And now an important component is the detector of single photons. Photomultiplier tubes do not work because they're in the photons are in the near infrared. Okay, if the laser is at 405, the downconverted photons are 810 nanometers. And photomultipliers are too inefficient at that level. So you have to buy special detectors called single photon detectors. And they are probably the most expensive thing in this system. And then you also have, well, we need to do something with the light, right? We create electrical pulses with the detectors. And then the other thing we need to do is to enforce this condition that we're dealing with pairs. The pairs are created at the same time. So to know that we are recording results that involve the pairs, we require the condition that the electrical pulses arrive at the same time. So we need a circuit that detects what is called coincidences. But then technology has helped us a lot these days. So you have these devices called FPGAs, field programmable gate arrays, that are not very expensive, and you can do all the manipulation of the electrical signals. Then everything gets collected by a computer, a regular computer. And then here's another example of, this would be at the high end of complication of some interferometer. And okay, so let's keep moving. Let's see. I need to move something here. Okay. One last thing is that I do have maintain an up-to-date website that has all kinds of information about this. So you can, I'll put that website at the end as well. All right. So now, after all this, let's do an experiment. Okay, so that's the apparatus. The source is here. One photon tells us that the other photon is doing something, going through the interferometer. And we know the answer. The probability of getting a detector in B, getting a photon at the detector in B is that one, as you see right here. And then, so if we change the path length of one of the arms, so what we do is we move very slightly this mirror, and then we apply a voltage. So here the horizontal axis is voltage that applies to some piezoelectric element that pushes the mirror very slightly to change the path length, and at the same time, consequently, changes the phase so that we can change the probability. And then what we do is we record the coincidences. So the signals from A and B go to this circuit, coincidence circuit, and we accumulate in steps of 1 second, well, in this case, 2 seconds. And there you have it. So as a function of this voltage, you see that the coincidences go up and down. That's your interference as a function of the voltage, or in the phase. So here's a time when I then ask the students, well, okay, so if delta is pi, then we're here, and the question is, where does the energy go? So I do make some videos for my classes, and normally I tell my students, okay, now pause your video and then think about this. So and then anyway, so I pose the audience, where does the energy go if delta is equal to pi? Okay, end of pause. Well, it goes to C, of course. Energy is conserved, so the light has to go somewhere. And if you calculate the probability, if you calculate with all the quantum algebra, what is the probability of going to C, you get 1 minus. And of course, if you sum the two probabilities, you get 1. So nothing is lost. And then we take the data, and then you see that the fringes are complementary, of course, because the total probability has to be equal to 1. And now here is a quote from Paul Dirac, which I don't know if some people could think of it as a cliche, but I think it's just very profound. And he said that the photon only interferes with itself. So each of the photons that go through the apparatus here, they interfere with themselves. And so then let's look at suppose this here, suppose we pick this voltage. So then here we have these number of photons were recorded at this voltage that arrived at B, and then these that arrived at C. So here's really the mystery for you right there. The photons go through the interferometer and interfere like waves, but they get only detected in one place, in either B or C. And here you see at that voltage, we get part of the time photons going to C, detected, no, not going to C, detected at C, and here detected at B. But they don't get detected at both places. And so you can also come up with a more quantitative way to say this, that we don't detect photons in B and C. And we measure the triple coincidence. And then there's this quantity called the degree of second order coherence. Again, it goes deep into the quantum optics theory, but it's calculated based on the counts that are received and the detectors. And if the photon goes to B or C, but not both, then this G should be 0. And if the photon somehow splits and goes to B and C, then you should get 1. And of course, you don't get 1, you get close to 0. Now, our students do this as a laboratory experiment, and then I'm showing there the data they took someday on their experiment. Okay, but now how about making the paths distinguishable? So here, we need to find a way to make them distinguishable. And what we can do is we can use the polarization of the light. These are all the possible states of polarization of the light: linear, circular, and then elliptical in any other places. And of course, the simplest one are photons that are orthogonally polarized, say vertical and horizontal. We could use right and left circular, but then that's more complicated. So we'll do the simplest thing. So here's what we're going to do. And then here is in the context of an experiment called the quantum eraser. So we create our photons. So our source is schematically this circle. And then we're going to put some element, optical element here called a half-wave plate. And when it is set to 0, some angular position, nothing happens. And so now the photons are produced by the source with some definite polarization, say vertically polarized. So then the light goes through interferometer, and if the polarization is not disturbed, then that's the probability. And then that's what we get when we do our measurements. But now look what we're going to do. We rotate this half-wave plate so that after the half-wave plate, the polarization is horizontal. So then the paths are distinguishable by the polarization of the light. You can say that the paths are labeled now because going through here, we're vertically polarized, but then going through here, we're horizontally polarized. So then there should be no interference. And we say that the paths are distinguishable, and then there you see the data. Now, those of you who are optics connoisseurs would say, well, the polarizations are orthogonal, so how are they going to interfere destructively? That is true. And but of course, we're talking about photons, and there are other situations where we can pull off the same, say, skeptical argument. And then we have something that is a kind of a quantum thing, which is very interesting to think about, and it's called the quantum eraser. So this is what we do. After the interferometer, we put a polarizer at 45 degrees. So what does this do? Then the horizontally polarized gets projected to be diagonally polarized, and the vertical polarization gets projected to be diagonally polarized as well. So then coming to this detector, the paths are no longer labeled. So we say that the information has been erased, or the path information has been erased. And so probability should reappear. And then here's a calculated probability. And then we do the experiment and we see that. And then one more thing about this result, and that is that this is one of the things about quantum mechanics. The quantum mechanics allows us to think this way, and that sometimes is very counterintuitive, because we are very deterministic in our thinking. We believe in cause and effect, so to speak, and so we're always thinking that if we change something, it has its own identity, and then we should know what is the end result. And in this case, we put this device that defines whether we should see interference or not after the light has gone through the interferometer. And then that's what could be a little disturbing for people if you're thinking in a deterministic way. And by the way, my students just love this experiment because it gets them there to think what the heck is going on. And then we did this experiment way back in 05. That's the data from there, but we keep taking this data over and over because, like I said, we have a laboratory. So we erase the information, right? But it's erased for B. How about C? If we don't put the eraser in C, what do we get in C? Well, we don't get interference. So there's this thought that in order to erase interference or superposition, one needs to disturb the system. We don't. We just need to manipulate the information. And okay, so let's keep going. Now, here I'm not going to show my data, but this is a very fascinating situation. Again, to do with quantum interference. So let's think about this. We have our interferometer, beam splitters, and then mirrors. So we should get interference, okay? But what if we don't have the second beam splitter? But think about this. So then here, if the photon follows this path, it goes straight to C. There's no interference. There's not going to be any interference because there's only one path. And if we go here, we go straight to B. So then one would think, okay, so in this case, the photon takes both paths because we see interference. But in this case, well, the photon, okay, quantum mechanics tells us how to calculate things, but then as human beings, we like to imagine, so what is happening here? So I'm just saying, this is one way, erroneously, of thinking, but it's one way of thinking. Well, the photon somehow makes a decision, or I split and get interference, or I either go this way or that way, and that's it. So somehow the photon makes a decision. So then there's this experiment that was done not too long ago that consisted in the following. And now this is following some idea going way back from John Wheeler called delayed choice. And so here's the situation. You have a photon, and then the photon is going to go through the interferometer. And initially, there's a beam splitter here and no beam splitter here. Now, after the interferometer, the photon goes through the first beam splitter, then we decide whether we want a beam splitter or not. And now, this is not a kind of experiment that we can reproduce easily, because the group that did this had an interferometer that was 50 meters long, right? So it's quite a challenge to do that. But there you have it. So the idea is whether after the photon goes through interferometer, then we decide whether to put the beam splitter there. So the question is, what do we get? And is there interference? And yes, there is interference. And there's the data from a photocopied paper, Jacks et al. In 2007, where you see interference when the beam splitter is there, and no interference when the beam splitter is not there. Now, question is, what happened here? And I'll tell you some idea, and that is, well, the photon goes all the way up to B and C, no matter what. And this is something that John Wheeler said, that what we measure is once everything is said and done. And he said, I'll get to that a little later. So let me show you something else. Well, suppose we do a double slit experiment with single photons, and then the same group did another experiment, beautiful experiment. And this is with single photons. And we may have seen these type of pictures before, that as we accumulate in time, we see more and more dots in our camera, and then you measure across the horizontal, and then you see indeed interference, and that the straight line is simulation, so everything accounts for interference. So let me ask the following question. So what are the dots? Are they photons or they're pixels? You'll be surprised. They're pixels. They're not photons. Photons occupy the entire interference pattern. Okay, let's keep going. Well, I mentioned about that to have interference, the paths have to be indistinguishable. And then we use polarization to make them distinguishable. So let's make them distinguishable in a different way. So suppose photons are in a coherent superposition of energy. They form a wave packet. Think of wave packet as that we don't know what is their energy to within a certain range. And well, through some analysis, when you have this type of situation, you get a pulse of light, which is a certain width. And then this is really, you can identify these are the Fourier transform of each other. So then what happens is that then the length, since the photon is going at the speed of light, the length of this pulse in space is called the coherence length. And now we could manipulate the coherence length. So if we have a wide bandwidth, we get a sharp pulse in time or space. And if we have a narrow bandwidth, we have a long coherence length. Okay. But now let me put this situation. So we have our photon wave packet pulse coming through, and it comes out. And then there are two possibilities. If the difference in length is less than the coherence length, that is less than the width of the pulse, then we can't tell from a timing perspective through which path the photon traveled. So in that case, that indistinguishability leads to interference. But now if the difference in path lengths is greater than the width of each of these pulses, the coherence length, then we would know which path the photon would take, because by timing the arrival of photons, we would know which path they would take. And in that case, there's no interference. So let's do the experiment. So we have the apparatus, and then we have these type of filters, energy filters, and we have the minimum length that we possibly can. Sorry, this is the coherence length, how wide in space the photon is if we were to somehow take a picture. And then the difference in path is less than that, and we see a nice interference pattern. Now, okay, the interference pattern is going to change. So how do we quantify it? There's this quantity called V that basically tells us how good these fringes are. So the fringes are smaller, then the visibility goes down. So here the visibility is 0.94. Okay, so then we're going to increase the difference in length. Okay, this is kind of like a picture, something we have in a picture in our head. What's the two wave packets relative to each other? They don't overlap exactly. So you can see that the visibility is not that great. And then it characterized by V now is close to 0.5. So we keep increasing the path length difference, and the visibility goes down. And we keep going. Here, 81 is, of course, much larger than the coherence length, so visibility is almost 0. Okay, so what do we do now? We change the filter so that the coherence length should be much larger, and we should recover the interference. And this is pretty standard thing to do. But what we do here is kind of more mischievous. We put the filter that changes the bandwidth on the other photon, the one that doesn't go through the interferometer, and then you get interference. And then this points out that something very special, that these photons are not really independent of each other. Once they leave the source, they're entangled. Well, of course, we connect them via coincidences. Okay, and okay, so then this is another experiment that we did just to make this even more extreme, which is introducing the concept of delayed choice. So the same experiment, interferometer, and we're going to play with the filters. But the only thing is that the photon that doesn't go through interferometer goes through a long fiber, 20 meters long, and then we pass it through the filter. And then the photon that goes through interferometer gets detected immediately, and then it goes through a long cable, electrical cable, well, so that the two photons arrive to the coincidence unit, so that the two pulses, electronic pulses, arrive to the coincidence unit at the same time. Okay, so then we do that experiment, and of course we use the short separation between the two arms, then the long separation between the two arms, no interference, and now we put the filter where we change this bandwidth with the light, and we see interference. But we put the filter after this long travel of the photon, but it's happening after the other photon has been detected. So when we decide whether we want to see interference or not, happens after the other photon has been detected, and which is pretty troubling. Okay, and we did this experiment and published it not too long ago. And but now let's digest this a little bit. Okay, this is the apparatus. Actually, we converted this into a remote experiment as well. So you have some motorized components. But now let's see what happens here. The choice of filter decides where the photon acts like a wave or a particle. But this choice is done by the idler photon, that is the photon that doesn't go through interferometer, after a single photon is detected. So you might be thinking, well, maybe this is action into the past. No, it's not. The photons are in a common entangled state of energy. And so then when a single photon is detected, the photon that goes through interferometer, you can think that both particle and wave information are stored in the data. And then when the second photon is detected and we require coincidences, then the filter decides, so to speak, which type of information we select to have available. And so in quantum mechanics, the measurement of each photon can occur at any time. The results are the same irrespective of when the measurements are made. This is a situation where we have to think deeply about what's happening. And even though quantum mechanics is somewhat agnostic about what we should get, by predicting probabilities only, it leads us to think more deeply about interference and about superposition. And then John Wheeler had this famous phrase, no phenomenon is a phenomenon until it's an observed phenomenon. We shouldn't say anything about what the photons until we have detected them. Okay, we were talking about really one photon going through the interferometer. Well, what about two photons? If we send both photons through the interferometer, what should we get? And now we put a beam splitter with detectors at A and B here, so that we could detect both photons coming out of here, and then detect coincidences between these two. Or we can detect coincidence between, say, I and C when the photons go to separate outputs of the interferometer. So let's see what we get. First of all, if we do experiments with one photon, then we get this type of interference pattern. I've shown it before. Let's move it out of the picture there. And there's two possibilities, so that's the probability. But now if we have two photons going through the same interferometer and coming out through the same port, say going to B, we're measuring the A-B coincidences, we have four possibilities. And then those four possibilities are not the same as two possibilities. So then they add in a different way, and you get this equation. Now, it looks somewhat the same, but this one has a square here and a quarter here. And if you look at the pattern, it's skinny at the top and broad at the bottom. So these two patterns are definitely different. How about the two photons going separate ways after the interferometer? Then you have 8 possibilities. These are all, you can see there in red, all the possible arrangements. And then the probability has a kind of a stark result here with this 2. So it creates fringes that are twice the frequency of the fringes of a single photon. And then it's said that these photons are almost acting like the parent photon, because the parent photon has half the wavelength. Okay. And then Glauber had a very insightful comment about this situation. He's saying, well, even if we have two photons involved in interference, the photons themselves don't interfere. What interfere are the possibilities or the amplitudes. Okay, finally, we're getting to entanglement. And so here we have a situation where we can create polarization entanglement. So think about this. We have a laser that is polarized diagonally. That is, it has two components. It has a component that is horizontal and a component that is vertical because it's diagonal. But now we have two crystals, and I mentioned that the outcome of the parametric down conversion is two photons being polarized in a certain way, in this case vertical. And but now if we put two crystals and one of them is rotated, then we can, oh, I don't want that yet. Then in one crystal, in one crystal, the horizontal component produces vertical photon pairs, and in the other crystal, the vertical component produces horizontal components. So we have really two rings. That's what you see there. But what is interesting is that one of the variables in this experiment is that if you tilt the crystal, you change the radius of the ring. So we can change the radius of the two rings because one ring is controlled by tilting the crystal in one plane, and the other ring is controlling the tilt of the crystal in the other plane. So we can adjust the two rings independently. Well, what should we do? Well, make them be the same. So then here we have it, indistinguishability all over again. If now both rings overlap exactly, we have no way to know from which crystal they were created. So then we have no way to know whether they're both parallel or horizontal. But now this is an intrinsic inability to know because we can't tell because they are overlapping. And so then the way to think about it is that now the source of is indistinguishable. So then we are in an entangled state. It's a coherent superposition of these two possibilities. And then this was, of course, first proposed by Erwin Schrödinger in 1935. Okay, so, but there's all these things that come with entanglement that are really fascinating that one could do. There's things about realism, and then there's non-locality. There's all kinds of interesting things for us to think about, and they're all relevant in quantum information and quantum computing. And so we can make an entangled state, and so the way to think about it, this plus sign is very special. It means being in these two possibilities at the same time, and not being in this possibility half the time and in this possibility half the time. So it's not a statistical mixture. It's really being both at the same time. And then the other thing is that then when you do a measurement, so we measure and we find one of the photons to be, say, horizontal, then we conclude that we're in this state after that measurement. Or if we get vertical, then we're in this state after that measurement. So a measurement of one photon determines the state of both. Now, the measurement of one photon doesn't determine what the other one is doing totally independently. That's not a good way of thinking about it. It modifies the state of both. And it is not equivalent to communicating instantly. Although this projection should happen instantly, it is not the same as sending information faster than the speed of light. But Einstein really disliked this, and he called it Spukhafte Firmung. That's my awful German. Spooky action at distance is a translation. But now we can probe in the laboratory between the two possibilities, entangled versus mixed, and there is a very easy way to do that. That quantum mechanics says that when you are in a superposition like this one, you're also in a superposition of being diagonal anti-diagonal. So you do an experiment with entangled photons, and you get where you put one polarizer at 45 degrees and the other one you rotate, and you get this curve, and then that's the probability. But if you have a mixed state, there's no variation with theta, and you see that. And then this is the apparatus, and then this is actually the apparatus, the remote apparatus. Then let me say a little bit about the remote apparatus, and we're soon to set this up so that anybody could really log in to our setup and do an experiment. And so then here we have it. We have a remote desktop, so somebody could come and actually make decisions. And so you would see in your screen a desktop, and then there's instructions for what to do. And then you will also have a camera, so you'll see the apparatus. You can see the laser when you turn the laser on, and so on. And then this one was for studying, for doing entanglement. And then we have some little circuits to turn things on, very low key if you want to do it yourself. We have motorized rotation stages because we need to rotate the polarization of the light. We can, if we do a delayed choice experiment, we need to change the filters, or in this case, we added some optical element to make the mixed states. And then we, of course, we control these through the serial port. It's pretty straightforward. And then we have some program that actually lets us do measurements, and everything remote. In fact, last semester, my students, it worked so well during COVID shutdown that last year that we were not in COVID shutdown, the students set up the apparatus, but then I had them do the experiments remotely. Okay, this is the last thing I want to say, and then we probably can be open for questions. And this is all this stuff that I've been talking about is fundamental stuff related to quantum interference and quantum superposition. And but here's something applied, and also something really, really fundamental, and that is that the act of measurement of a quantum state most of the time modifies the state. And that is really the key on this quantum form of communication. Something important is that involved in this is that quantum states cannot be cloned. So if you have a photon or anything in a given state, the only way to find out what the state is, you have to measure it. But in measuring it, you destroy that state or modify it, so that then you can't make a copy without destroying the original. So that is, you can't clone it. And then the technology involves that. So let's indulge just in this little end of my talk on what this entails. So think about this. We have a polarization splitter, and if it is vertically polarized, we get vertically polarized going through the polarization splitter with probability 1. If it's horizontal, it comes out at an angle with probability 1. Okay, so here we definitely can tell which state is by how it comes out of that polarization splitter. Now, if the initial state is diagonal, which is a superposition of horizontal and vertical, then there's a probability 1/2 of measuring vertical. There's a probability of 1/2 of measuring horizontal. And the same thing happens with anti-diagonal, because anti-diagonal is with a minus sign. And actually, the same thing would happen if we have a diagonal splitter and we send vertical or horizontal. So if we have a diagonal splitter, then when we send horizontal, we have 1/2 probability of measuring diagonal or anti-diagonal. Okay, and then Paul Dirac had a very interesting way of thinking about this superposition, and it is that when a photon is measured, the photon has to make a sudden jump from being partly in one of these states, 2 states, to being entirely in one or the other of them. So think about this. When diagonally polarized, a superposition of horizontal and vertical, then the photon jumps from being in this state to this state. And what is more stark too, which many times we take it for granted and when we study quantum physics, but if you think about it deeply, you get troubled, and that is that the probability is 1/2, but it's inherent. There's no way to know ahead of time whether detecting this photon will involve vertical or horizontal. It's truly random, inherently random. Okay, so we can use this principle to encrypt the communications and then get something out of it. I'll get into that. And so the idea is something like this. Alice sends a photon that is polarized in 2 possible ways: horizontal, vertical, or diagonal, anti-diagonal. Then Bob, the receiver, detects the photon in one of the, and he uses his splitter, so to speak, to detect horizontal, vertical, or diagonal, anti-diagonal. Since Alice can send in either of the 2, Bob can measure in either of the 2. And if Bob uses the same basis as Alice, so for here, so if Alice sends vertical and Bob measures in the vertical horizontal basis, Bob will get vertical. So if Bob uses the same basis as Alice, he gets the same state that Alice sent. But if there's an eavesdropper, since the eavesdropper cannot clone a photon, it has to measure it. So if it measures it in the wrong basis, for example, if Alice sends diagonal, the eavesdropper measures in horizontal, vertical, the eavesdropper gets vertical. So what is the eavesdropper going to do to not disrupt the communication and not be discovered? Sends the photon in the same state that the eavesdropper measured, will stay in vertical. But then if Alice and Bob have both the same diagonal anti-diagonal bases, then there will be errors when Bob measures this vertically polarized photon. So then there's a way to know that there was an eavesdropper. That's the main outcome of all of this. And of course, we did this laboratory demonstration, and that's the idea. We create, but now we use an entangled photons, and then we had to mimic Eve, and it's very okay. So now this is in the context of a laboratory demonstration. How do we demonstrate this principle in the laboratory for students? And well, it's very impractical to detect the photon that Alice sends to Bob and then re-emit it. That's just too difficult. But what we could do is we could mimic that effect of detection and sending by introducing a difference between the two polarization components that is larger than the coherence length, that it is almost as the two possibilities are independent. And so something like this, that so that you have, if you have a state like this, that is a coherent superposition of horizontal and vertical, this birefringent crystal makes them incoherent. And this idea was first put forth in year 2000. Although when we thought it, we thought we had discovered something, but then we realized that they had done it first. And then, so if Eve doesn't use the right basis, then as Alice and Bob, then Eve creates a mixed state, which is equivalent to measuring and resending the state in the wrong basis. And then that's the apparatus. Okay, I don't want to take too long, but we're really close to the end. And then that's the apparatus. And then this is Eve, just some thick piece of quartz. And the rest is the same as all the other experiments. And then we then make measurements. If Alice, Bob, and Eve, this is a sample, right? We did many. If they all three have the same basis, everybody agrees. Alice, Bob, and Alice and Bob don't know that Eve is there. But then if Alice and Bob have the same, and the same thing for diagonal, although we did have a couple of errors here. And then we had that, that in theory, Alice and Bob should agree 100% of the time, but then experimental imperfections led us to have only 92%. Okay. But now if Alice and Bob have the same basis, but Eve has a different basis, then there are all these errors. So, and then 25% of the time we should see errors, and we found 28% plus errors. So again, this is our demonstration, and then that's the apparatus. And then there's some considerations for this. So that leads me to the end of my talk. So there's time for discussion. So these are all students that have contributed a long way. Okay, here when we first got our apparatus and started developing these labs until just recently. And then we also had some collaborators over the years. And these experiments were done at Colgate University. And then that's in, the central part of the state of New York. If you're in New York City, you want to go to Niagara Falls, we're somewhere halfway, driving, of course. And then this work was funded by National Science Foundation over many years, actually. And then we have that there's this Alpha Society that funds these workshops that I do every year. So anybody's interested in these workshops, you get into Alpha, you can sign up, and then you get to come to Colgate, and then you get to start from scratch, clean breadboard, and then you are shown how to set the experiments up and do the experiments. Of course, I don't do those. The people that are the participants do all the alignments. Now, this is a picture of students in the quantum lab of 2018. And then because this is some kind of outreach that I do, that we have a lot of information on manuals, parts and prices, and this website. You can also send me an email. I'm happy to help whoever needs help. It's kind of, for me, it's kind of fun to indulge in solving problems, and it gets me away from administration. And well, I think I'm done. So I'll thank you for your attention.
Thank you, Dr. Galvez. I enjoyed your talk. I really, really enjoyed your talk. Thank you so much. Thank you for to the audience to be here. It was really interesting, and Dr. Galvez taught us about the different concepts in the next session questions. So we are going to start with session question. Please put your comments, your questions on the box chat, please. And we are going to start with Sebastian. Sebastian, please go ahead.
Yes, at the beginning, thanks for your talks. It was very nice. And we have maybe I note that we have 3 simpler questions and 1 harder question. The simpler question we could was about is quantum entanglement showed in your seminar similar or contemporary to double slit experiment? It was about how this quantum entanglement is connected with double slit experiment. So,
with a double slit experiment. Well, yes. I mean, all these experiments are connected because they involve 2 or more possibilities. So in the case of a double slit experiment, the light has to go through both slits to produce interference. But if we are sending single photons, we get this paradox that the single photon has to go through both slits. But then we detect only 1 photon, not half photons. And so if we go, to this experiment, this is a double slit experiment. So you have these researchers had 2 slits, and then they recorded that with the somewhat specialized camera to detect single photons, and it's the same, really the same concept. Well, this camera is very expensive, and sometimes these experiments can be, not very easy to set up quickly. So we opt not to do those. Actually, I do have a camera that I got with the grant, but I feel that the experiment with the 1 photon going through the interference and changing the interference not spatially but by adjusting the path lengths, that is more efficient, say, to see the interference. But really, the interference through an interferometer, like like this one here, that is the same as double slit.
I think that we can say that in double slit experiment we have the same quantum mechanics like in interferometry experiment. And the second question was about, is any interferometry used in any deployment quantum computers or communication devices? I think you.
Well, there are various schemes to make qubits, and actually, there's a scheme to make qubits using an interferometer, where the interferometer also provides a manipulation of the states of the photon. You can call it momentum states. But I don't think that people have thought of that in a practical way. People have proposed it and made some demonstrations, but an interferometer is kind of a free space interferometer. It is, it's subject to imperfections or you know, a lot of things that can happen in a lab. But there's a lot of groups working on embedding the light in optical waveguides, and in such situations one can use interferometers and do all kinds of path interference with the light, and then one could modulate these phases and whatnot with electronically. So I would say yes, that it can be used in the context of integrated optical circuits.
Okay, so the next question was, do predictability and unpredictability not both presuppose probability? It's maybe connected more with philosophy and of probability than mechanics, but what do you think about this?
So predictability and unpredictability, I think they're tied to probability, obviously, especially when the probability is not one, right? Probability is one, and so then you know it can be purely quantum experiment. If the probability is one, you can predict the outcome, but if it is not, then you cannot predict the outcome.
Yeah, I think in my opinion, the most important thing is that we devise things that are deterministic or probabilistic. Probabilistic if we don't know something about this, but deterministic if we can fully describe them. But this is, I think, in my opinion, some classical thinking about what is this. But the last question was harder, but connected with quantum mechanics interpretation. There was suggest that we should show quantum mechanics more by Bohemian mechanics called from Bohm interpretation than Copenhagen interpretation. What do you think about this?
I probably, you can see from my presentation that I'm thinking Copenhagen the whole way. I know of colleagues that are thinking of the Bohmian interpretation in a serious way, thinking about paths and some ways to mimic possibilities or states. But certainly I'm much more at ease with the Copenhagen interpretation, but I think that other views, if they predict the outcomes, I think they're equally valid. I mean, there's also the views about multiverses, right? And but I can't do anything about that.
Okay, if I can said, because the question is why we need classical interpretation of quantum mechanics, and what we mean by classical interpretation of quantum mechanics. This is the main question, in my opinion, and why we need, because what the beginning we should start thinking about what is classical interpretation, and this is of course the particles and waves. So we know even that you maybe not showed this purely in your slides, but we know that quantum mechanics is not a probabilistic theory in Kolmogorov science of probability. So this is the first things that I think that is important in this interpretation. And the second one is that Bohm interpretation is very nice in math, but there is some kind of topological part which is connected with all points and all time in space-time. So all this interpretation should have some, maybe not mistake, but some understanding points of view. So maybe Copenhagen interpretation is not good for everyone, but we should also think why we need classical interpretation of quantum mechanics. Of course, we know answer because it will be easier to explain what was happened, but it is nice because it's quantum mechanics, not it is not because it's classical mechanics or classical probability. It's of course my opinion. So if we have some more questions, Papier, could you tell us?
Sure, Sebastian and Dr. Galvez, we have one question from Farbot. Coach Note, please mute Farbot. Go ahead.
Hi, Professor Galvez. Thank you so much for the great presentation. Very informative. Can I ask, please, can you use, does it matter if you use a half-wave plate or beam splitter in the quantum key distribution? Is it the same thing or is it different? Because I have a kit that we use a half-wave plate to rotate the polarization sending from Alice to Bob. Does it matter really if you use a half-wave plate or beam splitter?
Well, the half-wave plate is known to rotate the polarization, right? I mean, that's what
Yeah.
what it's used, and so I use it to change the basis of because Alice has to decide horizontal, vertical, or diagonal, anti-diagonal, and the same thing with Bob. So now the polarizing splitter is some big piece of optics. It's difficult to rotate, so it splits the light by polarization, vertical, horizontal, and so then to detect diagonal, anti-diagonal, you basically rotate the input polarization. So if it comes diagonal, you rotate it. Okay, so you have diagonal and anti-diagonal. So if with a half-wave plate you rotate them like this, then the diagonal goes as vertical and the anti-diagonal goes as horizontal. So your polarization detection and switching the bases, you flip from one to the other by just rotating a wave plate.
I see, makes sense. Thank you very much. Thank you.
Well, thank you for the questions. We have more questions. Let me go with the the user Zoom color. He said, or she said, sorry. Could you talk about the hypertangled photon states, thereby encoding qubits in different degree of freedom? That's
right. There's a lot of possibilities with photons because they, well, especially with this source, where you can entangle not just in polarization, but you can entangle in other degrees of freedom. There's spatial mode. We've done a lot of work with spatial modes, but I didn't mention because it's just too much. But one can entangle in spatial modes. One can entangle in energy and momentum. So then the idea is that if you can maximize the entanglement, so you have all these other possibilities. So you have a qubit for polarization, but then you can have a qubit or higher dimensions for spatial modes, and the idea is how do you encode more information into a single photon, and a lot of people are working on that, especially with spatial modes. So that's where I'm mostly familiar, because spatial modes, that is the spatial form of the light. Well, we're used to a laser beam being just nice and round, but you can have other modes You can have a family of spatial modes called Hermite-Gauss modes. You have another family called Laguerre-Gauss modes. Laguerre-Gauss modes are nice because they have something very peculiar. Okay, they have the form of a donut, but then the phase varies with the angle, and so it winds up with the angle, and it can wind up from 0 to 2 pi when you go one full turn around the donut, or it can go from 0 to 4 pi, 0 to 6 pi, and you can go the other way. And all of those modes are orthogonal to each other, and they can easily be produced in the laboratory. So all of a sudden, instead of having 2 states, you have many states, and a lot of people are working on that. And certainly they are. People are getting, I think, some very positive results for communication. So you can have some kind of a multi-dimensional basis to communicate. And in fact, that is seen as the answer for increasing the bandwidth of our communications, because right now we communicate via email and whatnot, and then this communication probably is going overseas through underground, not underground, underwater fibers, right, all through the world. And the problem is that there's a finite number of fibers, and then with Netflix and all that, whatnot, we need to put more information. We need more fibers. But the idea is, what if we put more information with the fibers that we already have? And then one idea is to send spatial modes, in addition to all the other forms of encoding information, like polarization or phase. So I think definitely hyper entanglement, which is the kind of the word that means encoding as much information as it is possible in a photon, is kind of an interesting and viable idea, and which readily has applications for communication. I don't know if I answered the question, but
yeah, thank you, Dr. Galvez. In fact, we have the user Zoom caller who wants to reply. Please go ahead, Zoom caller.
Hi, Professor. I think you did a talk in the Caltech in May this year. Is that right? With Dr. Farbud Kushnod, who's also on the.
that's right.
Yeah. And I remember you were granting access to the lab. If you send an email, I sent you an email. I got a back and forth one email, but after that, the email chain died. My email was from Oxford University.
Oh,
yeah, so I think if you search, you will remember. So I think I really like the, that question was from me about the hyper entanglement. And I think, I think you covered the last thing about the position, phase, momentum, spin, polarized entanglement in that area. And, I mean, my thing was pretty much, you look at the BB8 protocol, which is, works on 2 bases. So essentially, this also opens up, this hyper entanglement opens up to multiple bases, because if you've only got 2 bases, you can actually predict one or the other, correct? Yeah, so if one base is not right, the Alice and Bob, can work on the other base. You only got 2 outcomes. But in a hyper entangled state, you could have multiple bases. Yeah, so my question on that was with regards to are you, aware of new protocols that are actually looking at it, and what's the latest and the greatest on that?
okay.
And also, if your lab access is still open or not.
Okay, 2 questions. The hyperentanglement, actually, I know of a group working on this by Ibrahim Karimi in the University of Ottawa, where indeed, if you are using a higher dimensional encoding basis, you gain some advantage. And I think right now, the let's say the barriers are technical. How do you best detect the different spatial modes? Then you also have, how do you put them in a fiber? That's another challenge. Fiber companies are working on it because they want to increase the bandwidth, and also, there was one more in just slip by, but let me answer then the other question before I don't wait thinking of it to come back. And that is, yes, I'm working on this lab, and in fact, I connected with a colleague, but turns out the university was getting nervous. Okay, so this is the idea: you have to log in to the university through VPN, and then the university was getting all worried about security. So we have the setup ready to be connected online, so to speak. And
I know you mentioned in the Caltech talk that, you know, if you guys, some of you want access, I can arrange that. And I was so excited about that. And I was emailing you back and forth. And I think I got a few emails, but then the email chain completely stopped. I think probably I thought security could be the reason.
Yeah, no. You should renew the email chain, and then we can continue. But I'm getting close to getting the university to figure out a system where they don't feel that the security of their network is compromised, and so that you can access the lab and do an experiment.
Great. And one last question on the same subject. I mean, you know, a lot has changed in this field. I mean, there's lots of background knowledge, which I'm so glad you provided in this talk that you're doing. Would you recommend to a lot of audience amongst us as well, some kind of a material that, or a book or something that covers from basic to what's the latest and greatest in this area at the moment? Maybe not today, maybe later on. I mean, I don't know. I'm putting you on the spot. Maybe if you can think of something, that'd be great.
Okay. Yeah, I'll think about it. I mean, there's some new textbooks that have come around in terms of starting teaching quantum mechanics with this linear algebra approach, kind of the direct notation approach. In some ways, they postpone talking about, well, if you're familiar with teaching quantum mechanics, teaching the particle in a box, they don't do that right up front. That's further later on. You have a book by Mark Beck. Okay, this is quantum mechanics textbook, which may not be exactly what you're asking, but this book is I use it for my quantum mechanics class that I teach, and this by Mark Beck. Then there's another book by I think David McIntyre that also has the same approach. And increasingly, there's new approaches to teaching quantum mechanics which go through the linear algebra type, talking about states, their interactions, rotation, time evolution, kind of things, before you get into really the Schrodinger equation.
Great, thank you so much. Lovely connecting with you again. Thanks.
Yeah, I have a question. May I?
May
I ask a question?
Just a quick question. Can you put that book names in the chat?
Oh, somebody did.
Okay, thank you. Thanks a lot.
Okay, my question is about John Wheeler and some conclusion from what he said. And he said also that the more we know how little we know. And I want to interpretation of this in the context of your talk, in the sense that the lab that you make available for people, will it enable finding some things that we don't know yet?
Well, I think what these labs do is make us think deeply about the outcomes of those experiments. It turns out that when you first set up this type of experiment in your school, the people that we be arguing the most about the outcomes are not the students, but the faculty, because really it shakes our understanding of all the fundamentals. So I think that I think that that's the value of the experiments, that it really, I'm not selling a particular version of quantum mechanics or a particular explanation, because again, it's my own explanation and people can differ. But I think that let's say, you can let nature speak for itself, and then try to think deeply about what it is that you observe. So so yeah, the more you think deeply about what is happening, the more you think that there's a mystery, and that it's kind of slippery to grasp, so to speak.
Thanks for the other quotes from John Wheeler, a very wise guy.
Oh, yeah.
Can I ask a question?
Sure, please go ahead.
Okay, you showed the single photon experiment where you're shooting single photons at the screen in the double slit experiment.
Right.
And you can see the individual photons hitting the screen individually without interference. And it's only over many, many photons that we get what is called a diffraction pattern. So how can you reconcile a single photon interfering with itself? How can you reconcile the wave-particle duality with the experimental result that we actually see individual photons hitting the screen in the double slit experiment?
Well, that is one of the points I was making. Well, you think about the experiment with the Mach center interferometer, where there are two outputs, only two, B and C, and really one way that I think about it is that there's a probability for the photon to be detected in B and C, and then again, Copenhagen, it's detected or collapsed in one of them, B or C. And so that picture of the double slit experiment, I think that, well, the dots that we are seeing are the pixels. They're not the photons. The photons, they get detected by the pixel. They didn't get detected by many pixels, but just one pixel, and that's why we see the dots. But I think that we have to think that the photon has a probability expanding through the whole screen, and then we detect it in only one pixel. We don't, yeah.
How do you separate the photon from the pixel? The pixel is caused by the photon, and it does not go through two slits. It only goes through one slit, or else we would see two pixels. We wouldn't, or more than one pixel.
Well, the dots are the pixels. The camera is giving you a pixel, and even, okay, so we remove the camera, we put a film. You still see dots, right? That is the photons are creating some kind of breaking a bond in the silver halide film. Okay, but my point is that that the pixels and the chemical particles of the film, they are the detectors. So you see that because so we see dots because our detectors are dots. Our detectors are the pixels. So we can't see the photon. We see the pixels. And I think the fact that we see an interference pattern tells us that because there's a probability that a photon will likely be at a maximum and unlikely to be at a minimum, it tells you that the photon is exploring the whole screen, so to speak.
All right, but we can only know what we observe. And
Right.
what we observe cannot justify the Copenhagen interpretation.
Okay. I mean, we can disagree, but I mean, what we observe is a pixel. We don't know that we are the pixel detecting a photon. That's what we observe.
But the camera detects a photon because camera does not detect electron or any other particle. A camera by default captures the light, i.e. a particle of light, which is a photon.
That's correct.
Yeah, but just
Okay.
in interaction, no
All
direct.
right, well, when you do the experiment with electrons, you can shoot single electrons and you get the same thing. It only the electron does not interfere with itself when it supposedly goes through two slits. It goes through one slit or the other, and it forms what you're calling a pixel on the screen, whether it's photons, electrons, or anything else. And because of this, I don't see how Copenhagen can be justified. Bohmian theory is justified by this, not Copenhagen.
Yeah, but it doesn't mean that it means just one thing, that all the particles, electron and photons, are not particles and waves, are something different. We just observed them by interaction, and we just could say that in one experiment you show that this is particle observed by particle, and in other experiment you can observe this object like in wave patterns. So,
by the way,
well, respectfully, what you're saying is influenced too much by Copenhagen, because at the time that Copenhagen was accepted as the correct theory, we could not do single electron or single photon experiments. So the only way they could interpret it was by wave interference. But the modern experiments dispel that.
But by the way, I'd like to just add that, whether you use an electron beam or a light beam, if an electron beam is without magnetic or electrical interference, it produces exactly the same diffraction pattern as that of a photon beam. A camera is the one that's able to detect photons, not electrons. Of course, you can have an electron detector, but the moment you introduce an electron detector, you're introducing, magnet or electronic beam, which actually changes the path of, because the electron itself is affected by those two properties. So I'm afraid that is not correct.
As soon as you introduce a macroscopic detector, you are changing the wave function. You're completely changing the system when you introduce a detector.
But a photon is not affected by it. But a photon is not affected by it.
But I'm thinking that when we send, we've seen pictures of an interference pattern, a double slit interference pattern of electrons, right? So the
Exactly.
electrons are interfering with themselves as waves, and they're detected as particles.
But you're interpreting it as a wave, because Bohm says that you get the same diffraction pattern if you consider the particles as particles and not waves. Bohm predicts trajectories, alternative trajectories of particles. That's how it's interpreted, and you coincidentally get the same, what you're calling a wave diffraction pattern, which in fact is traced out by individual particles, not by wave interference. It's an illusion.
Yeah, so thank you for your comment, your question. So we know this is a really, really controversial topic and really interesting. But in terms of time, we can continue with other two more questions that we have. Please feel free if you want to talk with Dr. Galvez. We are going to share the website and also his email. So let us continue please with two more questions. Dr. Galvez, if you feel good with this, is good?
Yep.
Okay, thank you. So first question is from Rabi Miñas. He said, can you say a few words about photon modes? Could one have n photon modes? And can your crystal show n photon modes?
Is he referring to spatial modes, or photon number?
Doesn't say. Sorry?
I can talk about spatial modes. I know some people have worked with photon number states. But photon number. Yeah, unfortunately, I'm not really an expert on that.
Yeah, he said photon number.
Yeah.
Maybe person who asked could clarify what you want.
Oh, no, he did. He did. He said,
Okay,
ask
so,
photon number.
sorry, can I butt in? Sorry about that. Sorry. Sure. If you can just explain the, what I was ready. I work in QC. Let me just give you a brief introduction. So we have optics computers nowadays using photon modes, and they use the term very generally. So, in the sense they have SDP, parametric down term conversion, and they have beam splitters, and they make qubits happen. So to drill down and just get a brief, in your crystal experiment, how do you get different photon modes, or can you get different photon modes, or in that sense? Thank you.
You mean the photon spatial modes, right?
Yeah. Do they
Yeah.
use photon spatial modes? And go ahead.
Yeah. So you can create. Well, it turns out that when you send the pump beam to the crystal that produces the photon pairs, because the mode of the pump photon can't be exactly projected onto a mode of the downconverted photons. Okay, so I don't know. That's a loaded answer. The downconverted photons are in a superposition. You can think at entangled state of modes where they're both in the. Okay, so there was an experiment done by way back by Zeilinger and coworkers in 1992 or 94, which was to send a beam and then investigate the modes of the photons that come out. So you're in a superposition of the both photons being in the fundamental mode, the so-called 0-0 modes, same as what you see from a laser. But then that superimposed with both photons being one with +1 angular momentum and the other one is -1 angular momentum. Now I'm talking then of these modes that are called Laguerre-Gauss modes, which have angular momentum, and that's a basis of spatial modes. And so then you got a superposition of 0-0 +1 -1 +2 -2 and so on. So just this source of down conversion can already produce that spatial mode entanglement with lesser and lesser amounts of the higher orders, like +3, -3, and +4, -4. But then the challenge is how do you detect them and harness that entanglement? Now, something that other people have done too is to, with these down-converted photons, you send them through a single mode fiber that cleans up the mode so that they are in the fundamental mode, the zero mode. Okay, and then you use some optical equipment to encode modes, like you can encode various states of angular momentum, +2 -2, +1 -1. You could create entangled states of polarization and then use the polarization as ways to convert the entanglement to some kind of entanglement swapping from polarization to spatial mode. So it might be an incomplete answer, but that's the spirit, that you can get spatial mode entanglement from down conversion.
Yeah, thank you, Dr. Galvez. We have one more question from Charlie Lee, and he said, in the first experiment, the probability of PB plus PC equals 1. Is it correct? So what is the physical meaning of PB and PC?
Well, it's a probability, right, that the photon goes from A to B the probability from A to C. But the thing is that the photon has to go somewhere or has to be detected by somebody. And so then the probability of the photon leaving and being detected by some detector has to be 1, right? Assuming that there's no losses.
Okay, we are closing the meeting, but first, Dr. Galvez, we enjoyed your talk. We have different people say thank you for your talk. Was really nice. We enjoyed. And we, for our audience, we share the website the YouTube channel. If you want to check the video again, we are going to upload there. And also, if you want to share, to take the slides, please write an email to Helen, and we share the email again. We are going to share again the email to get the slides, obviously, with the permission from Dr. Galvez. Okay, Sebastian, do you have any other question?
No question. Very great seminar, and we probably, with probability 1, finished today.
Yes. Okay, Dr. Galvez, thank you so much. Thank you. It was really nice. And do you have any share any other comment with us, Dr. Galvez?
Well, my only comment is that I think that there's definitely various ways to interpret these experiments, and then I think we have the let's say as researchers and physicists and scientists who have the responsibility to find out what's the answer. And I think first of all is the experiments are speaking the truth. We just have to interpret what they are. And I think the more we argue about what they mean, I think we're better off.
Perfect. Thank you so much. We are ready to see you the next upcoming meetings and events. Thank you, and thank you so much, and bye-bye.